This is a 4-stage electromagnetic accelerator I built.
Judgment!
An accelerator that launches a projectile with no moving parts.
The hardest part isn't building it, it is timing.
Each coil has to fire at the exact right moment. If the timing cheats even a little bit, the efficiency just goes to hell.
And right now, this thing is only good at
Destroying stuff. Punching holes the better none. While heating during the heating charge. Voltage draw before discharge. Small interference on infrared sensors.
Go away. Now I'll explain how this works.
Each coil is connected to a capacitor bank, and it sequentially creates a magnetic pulse that pulls the projectile down the barrel. The key thing is triggering the coil at the right moment. If you are too early or too late, the next stage can actually slow the projectile down.
I also designed the entire structure from scratch.
The case was modeled in Fusion and 3D printed. The power system consists of 4 capacitors, each 1000 microfarads rated up to 450 volts. Each stage is switched using a 70 TPS 12 thyristor, allowing high current pulses. To protect against voltage spikes I used 8 fast diodes. Here they are. The system is powered by an 18650 battery pack with a 3 SBMS protection system. Control is handled by an ESP32 microcontroller. Stage synchronization is based on signal from 4 phototransistors and 4 infrared LEDs.
At first, nothing worked, and it looked like this.
Why are my optocouplers not working? And then I had a genius idea. Check the datasheet.
Turns out my optocouplers just couldn't handle the current I needed.
The device also includes an IPS display for system parameters, a digital voltmeter for voltage monitoring, and a touch button for controlling the laser model. How measurements were done? First, magnetic field simulation, then prediction of optimal distance, and finally experimental testing. Calculated velocity 33 meter per second, experimental 35.6 meter per second, efficiency around 2%.
After building the model, I moved on to some experiments.
Velocity was measured using the time-of-flight method. 2 optical sensors detected the projectile, and the microcontroller measured the time of it in microsecond precision. And then I calculated kinetic energy and overall efficiency.
During testing, I also observed several side effects.
While heating during the period charge, voltage draw before discharge, small interference on infrared sensors caused by the coils. The experiment confirmed the existence of an optimal timing point, but also showed about a 70% drop in velocity compared to simulation.
And yeah, that's pretty much it. See you later.